Hi friends, we have a question here. A smooth sphere of weight W is supported in contact with a smooth vertical wall by a string fastened to a point on its surface, the end being attached to a point on the wall. If the length of the string is equal to the radius of sphere, find tensions in the string and the reaction on the wall. So we have got a smooth sphere having weight W. So let me draw that first. So friends, this is a sphere. Let's say the center of this sphere, this particular point is point P and its weight is W. So we have got a smooth sphere having weight W. So this particular vector represents the weight of the sphere. Now it is in contact with a smooth vertical wall. Okay. So this particular sphere is in contact with the smooth vertical wall. So as you can see here, this is a smooth vertical wall, friends, and this particular sphere is in contact with this particular smooth vertical wall. So let's say this is a point of contact and this is point Q, let's say, and the radius of sphere, this distance, let's say the radius of sphere is R. Okay, so we have got a sphere in contact with the smooth vertical wall, the point of contact being Q, the center of sphere being P, W is the weight of the sphere. Okay, so if you read further, this particular sphere is attached to one end of the string while another end of the string is attached to the wall. Okay, so here we know that the entire weight of the sphere is acting at point P. So your string should be supporting this particular point P. Okay, so when you connect the string, it should be able to transfer the load from point P to the string. So let me draw it. So if you see here, we have got a string over here. Let's say the string is attached to point L and the point M. Okay, now if you see here, so if you extend the length of the string like this, it is going to connect to the point P. It means the load from point P is transferred to the string. So always whenever you draw the string, it should be drawn like that. So in this situation, this particular load which is acting at point P is transferred to the string, okay, along this line. Okay, so this is a string. Now length of the string they have given, the length of the string is nothing but R again. Okay, as it is mentioned in the question, the length of the string is R. So this is the situation. So we have to find the tension in the string here. Since the string is supporting the weight of the sphere, so it should have some tension. So that T tension we have to calculate. Okay, and the second we have to calculate, friends, the reaction on the wall. So since this particular sphere is in contact with the smooth vertical wall, there will be reaction acting at this particular point. So we have to find the reaction at this particular point Q. So that I am going to call as RQ. So this is the overall situation what they have given us. So we have to solve this particular problem in order to find the reaction at point Q and the tension in the string which will support the weight of this sphere. So in order to solve this particular problem, now if you look at here, we can draw free body diagram of this particular figure. Okay, so let me draw the free body diagram first. If you carefully observe this particular situation, there are three forces. One is RQ, another is W, and the third one is the tension in the string. They are passing through the common point P. So it is a case of coplanar concurrent forces. So we can solve this particular problem with the help of Lami's theorem, but for that we need this particular angle. So what I will do is I will first draw the free body diagram of this particular situation. So let's do it. So first of all, I am going to draw the free body diagram, friends. Now if you see here, so this is the weight which is acting downward, same weight. So in free body diagram we don't show any kind of contact, so this contact will not be shown here. Only the force, that is RQ, will come. Now this RQ is acting towards point P, so we'll extend this in the same line. So this is RQ, so we can extend the force along the same line of action, and this is the point P here. Now the tension in the string we will show here at this particular point. So this is the tension in the string. If you see here, we have got three forces. They are passing through same common point P, and all these three forces are acting in the outward direction. So we can apply Lami's theorem for this particular situation. Now in order to apply Lami's theorem, we need all the angles between the forces. So here if you see, this angle is 90 degrees. This angle is also 90 degrees, friends. Now if I draw a vertical line here, this angle will also be 90 degrees. Now we need to find this angle. So this angle is not known to us. So let me call this angle as theta, angle theta. So if I can find this particular angle theta, then I'll be able to find all the angles. Okay, then I shall be able to find the angle between the tension and the weight W, as well as the angle between tension and RQ. So for that we will use geometry. Now if you look at here friends, in this diagram, this is radius and this is also radius, as you can see. So the distance between point L and the point P is going to be r plus r, that is 2r. Okay, and the distance between point Q and P is also equal to r. So if I call this angle as theta, so in triangle LQP, angle Q is 90 degree friends. Therefore, so if I use cos theta friends, so cos theta is going to be, by trigonometric ratio, cos theta is going to be the adjacent side, that is QP, divided by hypotenuse, that is PL. But QP is nothing but the radius only, the radius of sphere, that is r, and PL is going to be 2 times r. So this will turn out to be 1 upon 2. Okay, so from here if I simplify, I'll get angle theta as cos inverse of 1 by 2, and that is 60 degrees. So from here we got the angle, this angle as 60 degree friends. So we got this angle as 60 degree friends. So this angle will be 30 degrees from geometry. Now I can find out the angle between tension and RQ, which is going to be 90 plus 30, that is 120. Angle between tension and weight, that is 90 plus 60, that is 150. And angle between RQ and W, that is 90 degrees. Okay. With this information now I can easily do the calculation with the help of Lami's theorem. So let us apply the Lami's theorem here. So by Lami's theorem, so we will take tension here. So we will take tension T, divide by sine of angle opposite to it, that is 90 degrees. So sine 90 degrees equals, now weight divided by this angle friends, sine 120 degree, and that equals RQ, that is reaction at point Q, divided by sine of this angle, that is sine 150. So now answer must be in terms of weight. So I'll take this particular equation friends. So from there you will get, since sine 90 is 1, so we'll get tension equal to weight divided by sine 120. Weight divided by sine 120. Sine 120. So it is weight divided by sine 120. Sine 120 is root 3 by 2. So if you simplify, you will get 2 times weight divided by root 3. So we got the expression for tension in terms of weight is 2 by root 3 times weight. Similarly, if you consider these two terms, that is weight by sine 120 and RQ by sine 150, so you will get an expression for RQ, that is reaction at point Q. Okay, so let's do it. So I'm using this particular equation, that is RQ divided by sine 150 equals weight divided by sine 120. So this will give you the expression for RQ as sine 150 divided by sine 120 into weight. So this you simplify, sine 150 is 1 by 2 and sine 120 is root 3 by 2. So this whole will turn out to be 1 upon root 3, because sine 150 is, if you see, sine 150 is 1 by 2 and sine 120 is root 3 by 2. So 2 gets cancelled out, so 1 by root 3 will be balanced. So we can write down this as what? W divided by root 3. This is the expression for RQ friends. Okay, so we got expression for RQ as what? Weight divided by root 3, and the expression for tension as what? 2 by root 3 times weight. Okay, so this is how we can simply find the value of reaction at point Q as well as the tension in the spring. So if in any problem they have given you the value of load W, and they also give you sometime the length of the string, so accordingly you can substitute the values and you can find out the value of tension and the RQ. This tension as well as RQ will depend upon the length of the string which is given to you as well as the weight of the sphere. So accordingly, so whenever they will give you the value of load of the sphere and the length of the string, accordingly you will change the parameters and you can find out the value of tension in the string and the value of support reaction or value of reaction at contact point Q. Okay, thank you very much.